Okay, welcome to my webinar on what happens to displacement at the anti-resonance frequency of an ultrasonic transducer. My name is Hussein Shakani from Ultrasonic Advisors, and I'm excited to discuss this very interesting topic with you about anti-resonance and displacement. It tends to be confusing because it can be, and it was actually very confusing for me when I started off in ultrasonics. Actually, for several years, it was kind of a mystery. But today, I'm excited to clarify all of those misconceptions that at least I had and actually provide experimental data, not just hand waving per se. So the first thing we're going to do is I'm going to show an experiment. We're going to go through an experiment showing laser Doppler vibrometer and a frequency sweep, and you can kind of see some of the data already here. And I'm also going to discuss the displacement behavior at resonance and anti-resonance with respect to voltage drive. So I'll give some theoretical background too. But before we do that, I'll just introduce my company. So my company is Ultrasonic Advisors. I am a consultant helping companies to develop ultrasonic transducers. I think one of the best ways to describe me is I can pretty much help your company in all different aspects of ultrasonic transducer development, but I'm an independent consultant, so I can help you develop all the technology, the assembly, simulation, circuit development, but you'll own that product at the end. So that's extremely useful for companies wanting to own their own IP and development process. So I work on a whole host of devices like bolt clamp Langevin transducers, to atomizers, to different ultrasonic sensors, and do things from ideas to simulations, experiments, and beyond. So contact me through my website, or and there's all and book a call if that's relevant for you. So I'd like to now go through the background of the presentation. Basically, I guess this is the outline, but yeah. So basically, we know that piezoelectric transducers are electromechanical. Basically, the background, this slide is kind of saying why the topic, why am I even discussing this topic, and where do these questions come from, as like what happens at anti-resonance. So piezo ultrasonic transducers are electromechanical, so they're driven electrically, and we can understand, like, this is easy to know. Okay, at resonance, electrical resonance, there's more power draw, therefore there's more displacement, there's more mechanical motion. But what happens at anti-resonance here? Which is the high impedance state of a resonance transducer. The current is low. You might even feel like the power draw is going to be low. So what happens to displacement at the electrical anti-resonance? And what's the difference between electrical and mechanical anti-resonance? So I'm going to be describing soon that nothing special happens at electrical anti-resonance, actually. But there is a such thing as mechanical anti-resonance, and I'll talk about that near the end. But for most applications, it's not relevant, but it's very interesting, and it helps fill a gap in our knowledge about this whole idea of anti-resonance. So first, I'm going to go over the experimental setup that I use. I use a vibrometer, in USB, function generator, oscilloscope called the analog discovery, and a couple of other components to make it all work. So, but I actually measure the vibration using a laser vibrometer. I'll explain the experimental results and some more things about the setup, and then I'll describe theoretically what happens at displacement and electrical anti-resonance, like why the effect that we saw in the experiments actually happens. And then I'll end up talking about the difference between electrical and mechanical anti-resonance, and I will also provide data for that. And yeah, please go ahead and ask any questions that you have as I'm going along. Maybe I missed something, or maybe you're just curious about a specific topic. So in order to make all this work, so this is what the final experimental setup looks like. We have our vibrometer here, which shoots a laser at this transducer, and it measures the displacement through its different signal processing, optics, and electronics. And we have our transducer here, and we have an analog discovery, which is a USB oscilloscope and function generator, which also has a sweep function, which we can use to measure impedance, and also the displacement response. And there's actually a circuit here that I'm going to show in a second. But the circuit that I put there is has a specific purpose. And but I'll describe that in a second. So here's the 40 kilohertz cleaning transducer. It's just the run-of-the-mill common one you can buy for pretty cheap. And here's the analog discovery. And you'll notice that I have a circuit interfacing. So the analog discovery has a 5-volt output voltage that you can apply. But as you know, and I'll just kind of jump here. This is the impedance response. You're going to get a lot more power draw at resonance from a constant voltage drive than anti-resonance. I think many of us understand that. So in order to even out the power, so that I don't have like really low displacement that I can't measure, I kind of have you could say an impedance, a balancing circuit that will allow me to have more or less constant voltage, constant power draw. So when the current is high, the voltage driving is low, and when the current is low, then the voltage will increase to get the power back up. And I'll explain that in a second. So with this power, kind of leveling, which is required to actually have enough displacement to measure across all frequencies, and also so that we're not like driving the anti-resonance with really teeny power, and we're driving the resonance with a lot of power. So it's not a good theoretical experiment if you have different conditions all around. You're not able to isolate the thing you're trying to understand. So here's the breadboard. Basically, there's the waveform generator, which is called W1 of the analog discovery. So this and you can kind of zoom all the way in here. There's these breakouts. So this is like waveform 1, waveform 2, signal channel 1 minus channel 1 plus. So this is like semi-differential actually too. So there's no ground reference on the outputs on the measurements. So here's the waveform 1 in the ground on one side of the transformer, the low impedance side. On the high impedance side, we have our crystal, which is basically our transducer here. And we have this 100 ohm resistor that's used to measure current. This 100 ohm resistor also helps to reduce the current spike, which is going to happen if you drive a constant voltage across this piezo. So that's for the impedance measurement. So the program itself that comes with the analog discovery is called Waveforms. It has this frequency sweep capability, measures current and voltage using a circuit like this, which I created, and then it gives you those values. But I can also take off this plus and minus voltage and use the vibrometer measurement instead. So in this case, I'll give it a thumbs up here. Why not? Does it work? I don't know. Okay. So I can use the second channel 2 for the vibrometer measurement. So now I have voltage and the vibrometer measurement. And the thing here now I have a stable comparison. So I have voltage being constant in both cases, channel 1, and channel 2 is the only thing that's changing. So I can, now I have frequency sweeps for voltage to vibration and voltage to current. And note that the voltage, although it's going to be changing across the frequency sweep because our kind of impedance balancing, and obviously it's going to be low at resonance and high at anti-resonance because the impedance differences, we'll have that track, and it'll be the same for both cases. So we can compare our two plots that we're going to do, which is going to be impedance, which is basically voltage and current, and also voltage and displacement. Voltage will be a constant because the way I set up the experiment and I set up the probes such that there's no math channel like that you need to subtract. So that subtraction is not going to happen. Typically within oscilloscope, normal oscilloscope, you have to reference to ground if you're using normal probes. And if you have to reference to ground, then your voltages are going to get messed up because you're going to need a math channel for voltage measurement. So you have to use all these different settings and stuff, but we don't have to do that here. The transformer I used is a audio transformer, and I showed it in the last webinar. It's a 5:10 transformation ratio. It's an iron core laminated, so it's not really good for high frequency, but it's not bad either. So it's just basically used. I'm not trying to deliver a whole lot of power. I just want that voltage to even out. And as you might know, if you put a low impedance load on a high impedance output of a transformer, you're not going to get a whole lot of efficiency or power draw to your target, which is actually what I want. I want it to be inefficient at resonance, give low power resonance, and give decent power at anti-resonance. So that kind of balances everything out. And so the goal, again, keeping power approximately equal between resonance and anti-resonance. So basically, I have 4 volts applied from the analog discovery to the transformer. And so when the impedance is high, the voltage will be allowed to get to the highest point. So if it's 4 volts, it'll be 20 volts, right? AC. And if you have a low impedance, then it will be really low. And I'm going to describe that. We're going to show plots. And this way, the power is sort of constant across all the different impedance ranges. That's good. I'll give that a thumbs up. All right. And this, oops, okay, perfect. I should lock it. So this is the vibrometer that I used. It's called the Motion Go vibrometer from Omnisensing Photonics. And it has an analog output. It also connects directly to your computer. So if you want to read values from that, you can. But obviously for my frequency sweep, it's going to be so much better for me to use the same data acquisition system that I use for current. So I can just plot all that together. And I hope all that makes sense for you all. Now experimental results. So I have this experiment. I run frequency sweeps. In one case, I just measure impedance, basically current across that resistor. And then in the second case, I measure the output from the vibrometer. So I have 2 experiments here. Easy presentation, right? If only all presentations and scientific work can use 2 experiments. All right, so we're gonna go here. Impedance. This is something you guys and all of these things here showed. They're the actual settings that I use for doing this test. And I'm going to attach my actual waveforms file. So if you want to like dig into the data and see what I was doing, you'll be able to do that, and it'll help you recreate the results. So here we have impedance. So we have the resonance here about 39.7 kilohertz or so, and the anti-resonance is about 42.7 kilohertz. And here's the phase, just completely as we expect, -90 to 90 degrees. All right, so this is like your normal anti-resonance kind of system. Sorry, normal resonator. And here's voltage and current. Now this is where it gets kind of interesting, because I have that circuit there. The voltage and current are definitely not going to be constant. And mind you, they're not even constant, or the voltage is not even constant on a traditional impedance analyzer. Otherwise, you drive your 1 ohm load with like 1 volt, you're going to get 1 amp over your like test device. No, your impedance analyzer has an output impedance. But in this case, with that transformer, I really even it out much better than even just a plain resistor or plain output impedance would. I also want to mention one thing while we're at it, is that I did end up having to use a 5 volts DC supply additionally to the USB power source from the computer. Putting a 5 volts supply on there allows the waveform generator to actually work in the conditions that I allowed it, that I asked it to work. Because although we'll be drawing like milliwatts or even microwatts over our transducer, the analog discovery is actually perhaps putting out hundreds or at least like 100 milliwatts probably of power just to drive that empty side of the transformer, which is almost like short-circuited in a way. So here's the voltage, and we see at resonance it's getting close to 100 millivolts, but at anti-resonance, as we get farther away from the resonant frequency, it exceeds 10 volts. It gets probably closer to 20 volts. This is a log scale. And here we see a constant current of 10 milliamps, and then at anti-resonance, it's 100 milliamps. But basically, by putting that circuit in there, we keep the power constant. Now, power calculations are a little bit tricky here, because when you get phase values close to 90 degrees, you will not, it'll be extremely sensitive to the phase value, right? Like if you have like 0.2 degrees error in your phase measurement, you're going to have a huge error in your power measurement. So just take it for as a, with a grain of salt. This dotted line down here, so this is the actual power. This is the real power. So this has the cosine value, the cosine theta value. This right here is just V times I, RMS. So, but basically this includes the phase. So you can look at resonance here and anti-resonance there. Apparently it drawed almost 1 watt between those two. And between those two, in those frequencies, and between them, it didn't draw less than 100 microwatts. So at least there's only perhaps maximum a 1 to 10 difference, although I don't precisely believe it. There's probably higher power here than it's actually accounted for. And this like power minimum here is probably due to the kind of phase kind of problems. But noting that these frequencies and everything here it's kind of stable. And that was my point here. So this is not a circuit precisely optimized for power measurements at close to 90 degrees. Now we get to the special part. With I use the displacement. I measure displacement with at the vibrometer, and you have to set up the vibrometer with special like kind of functions. So is the graph voltage current? Is the voltage constant at anti-resonance? So somebody asked. So it's approximately constant at anti-resonance. This is voltage. So somebody asked in the comments, is the voltage constant at anti-resonance? And it's approximately constant, so it changes only slowly. So the anti-resonance is about. Sorry, I should just use this feeling. So the anti-resonance is here, so it's approximately constant. Why? Because the impedance value is high and it's staying high. So the impedance value is not going. Let's assume that the output impedance is actually 1300 ohms, like that data sheet of the transformer was saying. And then in that case, and I'll use spacebar to move. In that case, since we have like almost 100 kilo ohms, like after you get to past a certain point, you have a very large load. So if you have a very large load, you're not going to be changing your load impedance for practically with regards to the transformer. So it's constant. So is anti-resonance better for ultrasonic cleaning? I guess the answer is like a good consultant would say, the answer is it depends. But you can hold that kind of question, and I'll kind of get to it, like application wise. What does all this mean? So we're going back to displacement. Now, I directly connected channel 2 to the analog discovery. The analog discovery thinks I have a 100 ohm resistor and I'm measuring current. So basically, it's gonna think current is the measurement from, and I'm gonna do conversions later, but right now I'm not doing conversions just yet. It thinks the analog output or from the vibrometer is actually current. So if the current is high or the analog output is high, then the impedance is low. So with that, let's look at impedance. So now I added the displacement. The displacement is in blue. So this here, and I can even get the blue. I have a very similar blue to that. Blue. This is displacement, and the orange is Z. But this is not just displacement. This is displacement divided by voltage, and obviously impedance is voltage divided by current, and these are magnitudes, right? So at resonance, we see here. So this is the whole this is like the climax of the presentation. One of the climaxes. At the resonant frequency, we see that the voltage to displacement value is the highest, because this is if the voltage over displacement is low, that means displacement over voltage is high. So the lower the impedance, or the lower this kind of pseudo impedance, basically the higher displacement we're going to get. We're going to get more displacement from the same voltage. And as we leave resonance, we don't see anything at anti-resonance here. There's no special feature of the displacement. Displacement continues to drop lower and lower according to the voltage input. And this becomes easier to see with admittance. Admittance is 1 over impedance. I'm just going to draw all that out. So this is displacement divided by voltage, and this is basically impedance, which is, or admittance. So admittance, which is current over voltage. So obviously the current is highest over voltage at resonance. That's why you have a peak here. But as we get away from the resonance frequency, our amplitude goes down. And this little peak here is actually a real phenomenon. This often happens in ultrasonic transducers where you get like different kind of small peaks or different occurrences around the resonant frequency or even the anti-resonant frequency. But here, we see no specific trend. So it's like the displacement doesn't even know. And everything here is normalized. So it's not like, oh, your experiment was wrong. It's all normalized. These are ratios. So displacement actually shows no, it doesn't even notice that there's an anti-resonance frequency there. So that's kind of interesting. So anti-resonance, so displacement does not even see the electrical anti-resonance at all. And let's just continue with finish this part here. Here I actually did the conversion. So this is microns per volt. So this is microns per volt now. Oh, actually, this is not or this is meters per volt. Meters per volt. And this is actually the correct conversions. And obviously, if I corrected the conversions for the displacement, the electrical values are going to be wrong because it's the same plot. It does all the same kind of analysis. But take a look at, so we have about here, we have almost 1 micron per volt at resonance. 1 micron per volt. Almost, like, let's say it's like 0.7. And at anti-resonance, there's like something like 7 nanometers, like maybe like 7 nanometers per volt. At anti-resonance here versus here. But mind you, that's going to change a lot when you start adding damping. You're not going to have 0.7 microns per volt. And as you actually also, you get past the resonant frequency, this is, you know, as you add damping, your off resonance displacement is still relatively constant. The bandwidth starts to increase, the peak starts to decrease. So you actually get a little bit higher off resonance displacement in an actual application than actually the transducer just sitting in air. However, it will be very stable, this ratio between voltage and displacement. So you can drive your transducer to anti-resonance, you can locate it electrically, and you'll always have this value 0.7 nanometers per volt. All you have to do is select the correct transformers in order to deliver that high voltage, but you'll draw the same current or power from those two methods. And here I'm actually plotting yeah oh yeah, one other thing I forgot to mention, sorry about that. Here's the phase values. So you see, again, this is a displacement, basically voltage over displacement phase, and this is current. Here we go. Voltage over current phase. So we see obviously impedance negative 90, 90 goes back down. But however, if the phase of displacement only changes 1 time at resonance, it doesn't see anti-resonance. This is another reason why, like, okay, the data is correct too, because it doesn't even change phase either. I'm not nor does it change phase, or does it change, because phase is always a relative number. It's you'll get the same phase even if there's no normalization for phase. So, but the only thing here is you're going to notice that the values that usually for a vibrometer, and this is important, if you use a vibrometer, you have to correct the phase values for how you are situated and oriented. You should note, and it's pretty obvious actually if you draw it out. Maybe I'll just draw it out one more on the note. And I'm gonna I'm going to decrease this size here so I can actually draw. So if you have, that resonator, and we're using phase, and you just describe a very simple mass spring damper. Save a mass. You have K, and you got that dash pot here. So for this, in this case, if the forcing function is equivalent to the voltage, kind of voltage times the piezo constants or something. So the forcing function and at resonance, the forcing function is in phase with the displacement. Like if I'm pushing a block very slowly up and down, like everything's going to be in phase. So you should have zero phase at low frequencies, at resonances. And then what happens is 90 degrees, at 90 degrees exactly, this is our resonance frequency, and it gets to 180 after that. It's like you're pushing it. So basically what this means is that if this is displacement, well, what happens to velocity is the velocity is a cosine, right? So velocity is lagging, you could say, displacement by 90 degrees. So velocity actually starts at negative 90. It gets to 0 at resonance, and it goes to 90 after you pass the resonant frequency. However, if you change your voltage probe leads, then it'll affect how your crystals are polarized, will affect how this switches. But you should know that at low frequency, you're going to have 0 phase. This is obviously not the case here. So you would probably have to like add 180 degrees to the phase, and then that's probably what's needed here. But you can see it's fairly constant across this range there. So I hope that makes sense and helps. So let's actually look at the real displacement in both of these cases. So in this bottom plot here, I actually calculated the actual displacement. Just like above, I did the actual voltage. I showed the actual voltage just to show how constant I got. So this is the actual displacement. So this right here, about right here, is the anti-resonance, and here is the resonance. Or sorry, here's the anti-resonance. This is I'll just write R, and I'll just write AR. So we can see there's actually perhaps slightly more displacement at anti-resonance than resonance, which kind of makes sense because we have that high output transformer, and it's really poorly works at resonance. And these are absolute values right now. So I approximately got but I did get kind of a similar, like if this maybe is like 110 nanometers or 10 nanometers there, this is probably like 90 nanometers here, or 80 or something like that. So they're approximately equal. And so my goal of keeping the displacement about the same without any special like feedback loop is great. It worked. Hooray, pretty much. That's what I like to say. So why does displacement not get affected by the electrical anti-resonance? The easiest way I can show it to you is using the equivalent circuit. And let's get like a bigger pen here. So this is the really, I think this is the easiest way to show it. So this is the mechanical branch. This is the LCR circuit, and this is the pure capacitive or pure dielectric branch of the circuit, which has nothing to do with mechanical, you could say. So this part here is responsible, if you're thinking about impedance, it's responsible for this dip. All right. And if you only had this LCR, you would actually go back up. So this actually approaches infinity. And as you keep going, as you go infinite, as you go infinite frequency, you end up, this inductor takes over, or basically the inertia takes over. The inertia is so much you cannot even move the thing. There's no current generated. However, because of this parallel, what happens is that as you get over the resonant frequency right here, you just pretty much have this inductor and this capacitor here, because after the resonance, the only inductance goes, and then this capacitance resonates, anti-resonates actually with that inductive value, so you get an anti-resonance frequency. So this anti-resonance is caused purely by electrical means. What this actually also means is that if you add an external capacitor, you will shift the anti-resonance backward, and the displacement still won't care. So you can actually add external circuit components like especially a parallel capacitor. You will shift the anti-resonance frequency without changing anything mechanically about the system, and it won't even affect. And again, this is this is kind of the thing shown here, where the displacement in blue is not affected at all by anti-resonance, because the anti-resonance is caused by the capacitive behavior of the transducer. It doesn't affect the mechanical resonance phenomenon. That being said, the anti-resonance is very useful for power delivery, because it is a real resistive load. So it's very useful for power delivery. And it's nice that it's not at resonance, because it's much more stable of a displacement. So if you put 500 volts at anti-resonance, in a loaded and unloaded state, it'll approximately have the same displacement. That's not true for resonance. Resonance, if you put 20 volts at resonance without a load, you probably have to put 100 volts at resonance with a load, because of the constant. So it's very good for like a very robust electrical system that you don't need a lot of complex feedback for. Nowadays, you can, that kind of feedback system is not elusive, but certain applications like welding, which have very different mechanical conditions, they they do still use this anti-resonance behavior, and sometimes it's easy to get a high voltage, especially when you're working with AC mains. You have access to high voltage. You're not running from like 5-volt like power supply or from the wall. You have access to the rails of your kind of central power supply, like whatever 220 volts or 120 volts AC. So finally, I want to describe the difference between electrical and mechanical anti-resonance. So mechanical anti-resonance, what is it where the mechanical displacement is lowest? It actually exists. All right. So this is the resonance sweep from 38 kilohertz to 50 kilohertz. You'll see in the and this is admittance, or this is actually, yeah, this is admittance here. We'll do admittance. This is admittance. So this is and let me know if something's not making sense here. This is admittance. You can sell the units or Siemens. So this is a resonance frequency. This is the anti-resonance frequency. And here, this is the resonance. This is the second mode. This is the anti-resonance frequency. You see the same thing. Okay, we have this peak on displacement, and it doesn't really care about the resonance, or it doesn't really care about the anti-resonance. It doesn't even see it. Just goes right past it. But here, it's kind of strange that we have a minimum displacement before this resonant frequency. And this minimum displacement is the mechanical anti-resonance here. This is the mechanical anti-resonance. And I'll probably write in the same color. Mechanical anti-resonance, where you have displacement being the lowest. This happens because of destructive and different interferences which occur. Here's the values in microns or meters per volt, and here's the units there. But as you see here, there's a minimum displacement. You see something funny happening with the, not funny, but it's not hilarious funny, but like interesting funny. There's a minimum that the phase changes back at this mechanical anti-resonance. So the mechanical anti-resonance affects the phase, and then it comes back up. It goes back up through this resonant point here. This is the resonant point, our traditional resonance, and then it goes again flat. And we know this should probably be 180 degrees, so you probably have to shift that if you want it to be real or actual, what it is. So, but it also depends on how you orient your probes. So this is the mechanical anti-resonance. It exists. So what does that basically mean? So let's just take a bar. what does mechanical antiresonance actually mean? So let's take a bar, and maybe some of you are used to seeing like, okay, this is the spatial coordinate, and this is the coordinate of microns, let's say. So the first resonant mode, longitudinal resonant mode, looks like this. So this is called a half wave, which because it is a half wave. So this is called mechanical resonance. And mechanical antiresonance, that happens when you have at the frequency at which, and you can, for a bar, you can actually predict what frequency this is going to be, at the frequency at which this occurs. So this is actually this is a full wave. So we know that full wave, there's no full wave free resonance, free resonator. So this is like a piezo bar, like it looks like this, like or like a plate. All right. So it looks like that, or you can even say it's a rod if you wanted to. But the mechanical anti-resonance is actually minimum displacement. It's not ever going to get to purely zero, but there's minimum displacement at the tip simply because, working with the speed of sound and the frequency. Well, we're going to have the frequency of the full wave, of 1 lambda, a wavelength is going to be a mechanical anti-resonance for a free resonator. Now, our normal transducers are not really symmetrical and things like that, so you're not going to be able to use this like wave speed to determine it. But for a D31 plate, you can actually like calculate that. This is so the next mechanical resonance will happen where you have, how does it look? What does it look like? This is displacement again, like this, right? It's gonna look like that. So this is a 3/2 lambda is the mechanic, and because this mechanical anti-resonance is not actual it's not increasing the energy stored in this thing. You will not see any special thing happening in impedance. You cannot detect mechanical anti-resonance with impedance, as you see here. This is admittance. This is admittance. So this is the resonance. It doesn't detect mechanical anti-resonance because because even at off resonance, the capacitance is dominating unless you have some interaction between the inductive and capacitive qualities. In that case, you have an anti-resonance. But if it's not resonance and it's not anti-resonance, then it's going to be dominated by the capacitor of your transducer capacitance, because as frequency increases, capacitance impedance decreases, so it dominates the current flow, so you won't be able to see it. But if you were to do some inductive stuff, then you might be able to get there. All right, so I'm going to wrap it up now. Here in summary, the anti-resonance is electrical only phenomenon, but it's very useful from electrical drive perspective. It's a very stable frequency in terms of voltage to displacement output, with loading or without loading. And so I use both vibrometer and electrical data to study the anti-resonance fully, and the resonance in this case. So the mechanical anti-resonance is a real thing, but it's very different from electrical resonance. And for most applications, it's not, I think pretty much for all applications that I know of, it's not useful, but it's interesting to predict, and it can maybe be used to verify FEA work. But beyond that, I don't think there's a use for it, but you should know that exists. Because otherwise you'd have a misunderstanding, and who wants to have a misunderstanding? All right, so I think so I don't think there's any remaining questions right now. So I thank everybody for coming to my presentation on displacement. Of resonance and anti-resonance. I'm going to be continuing some displacement stuff in the coming weeks. So I look forward to seeing you all there. If you have comments, questions, suggestions for topics, I want to hear them, especially if it relates to the topic I'm doing, because typically I like to keep the same kind of stuff going. So while I'm doing that, but you can also just mention anything. Next time I'm going to be sometime soon I'm going to be comparing how do you understand the linearity of a vibrometer. The vibrometer is right there. That's why I'm saying that. And how do you measure the accuracy? Because like you don't have like a resistor standard or something. How do you measure the accuracy of vibrometer? And what other things are useful to measure vibrometer and the transducer? What things can you learn? What can you tell for quality analysis? I'll be doing all that. So Thank you so much and see you in the next webinar.